Swings are cool and all, but what if the strength of the string isn't as strong as you are? Today we're here to learn the scientific reasoning behind how I got myself into this particular situation. In order to answer this question, we're going to have to go over a few basic principles of physics first. First of which being Newton's second law of motion. So Newton's second law states that an object's net force is equal to the mass of the object times the acceleration. It can also be written as the acceleration is equal to the net force over the mass. Either or, just basic algebra. So in a circular object path, though, it changes a little bit because there's a new force, the centripetal force, acting towards the center at all times. And this is written a little different. So the centripetal force is actually equal to the velocity squared over r, the distance of the object from the center of the circle. Now this is important because these two equations relate to each other, and since it's both acceleration, we can actually set them equal to each other. So the net force over the mass is equal to velocity squared over r, and this means we can find any variable in this equation. So we will be looking for the net force, which ends up being equal to the mass times the velocity squared over r, because in the net force, that's where the force of tension is. And when the force of tension is the greatest, that's when the swing has the highest chance of breaking. So if we draw a big model of our swing at several different points here, they wouldn't really go upside down, but we're going to use it for this example. So let's start at the top. The forces we have here are the force of tension going down, the centripetal force going down, and we also have the force of gravity going down. So by using our second law of motion here, we can make an equation that states that the net force, which is just mass times acceleration, so that's really centripetal force times the mass, is equal to, since t and the acceleration are going down, we know that this has to be a negative value, and this is also negative t minus mg. All these are negative. So we have to move this over to find t in order to isolate it. So we end up having t is equal to mass times the centripetal force minus mg. So this is subtraction. So this is going to be a pretty low value up at top. Now let's look at that in comparison to one other side. We've got the tension going towards the center. We have the force of gravity going down, but we also have the centripetal force going towards the center. Now, since this is going down, it's not really affecting the tension because the tension is going towards the center of the circle. This means that the tension is actually equal to the centripetal force. So it'll be mass times velocity squared over r, back using this again with the net force. And you can already see that this value is bigger than this one because this uses subtraction. This is this value minus mg, so this is already bigger. And down here is actually the biggest value because we have tension going up, centripetal force going up, and then we have the force of gravity going downwards. But by using Newton's second law, we can see that the force of tension is positive, the centripetal force is positive, so what we end up having is the net force is equal to positive tension, but we have negative mg over here. Now, when we see this equation, if you isolate t, you end up having, we know that this is mass times acceleration, so mv squared over r plus mg. Now, we can clearly see, compared to the other two, this is the largest one because we're taking two values and we're adding them. Now, over here is subtraction. Over here is just one value. Here there is two values being added to each other. So the bottom is clearly where the most tension is, which means the string is under the most stress, and that is why I fell onto the ground when I hit the bottom of the swing's rotation.
Oh.